Hello and welcome to the AICE Chemistry lecture series. In this video today we're going to look at chapter 14 section 2, which is going to focus on homologous series of organic compounds. So it's just a very short section introducing the idea of a homologous series, what it is, and how do we see it come up on the exam. So let's get started. So a homologous series when it comes to organic chemistry refers to a compound or a series of compounds, should I say, that have the same general formula, meaning they have the same functional group, but they have an increasing or decreasing number of carbons. So let's start with, before we talk about this, what is a functional group? We discussed how in chemistry, in organic chemistry specifically, all the compounds that we see are going to be some combination of a carbon-hydrogen backbone, so a bunch of carbons bonded together, with hydrogens attached to them and some other compounds. So all organic compounds are going to have carbon and hydrogen. But whenever we add something new, we call that a functional group. A functional group is an atom or group of atoms in an organic molecule which determines the characteristics of the chemical reaction. So for example, if we have a carbon with an OH sticking out of it, we will call that an alcohol. If we had a carbon with a halogen sticking out of it, we will call that halogen alkane. If we had a carbon that's triple bonded to a nitrogen, we will call that a nitrile group. So these are functional groups. They're essentially anything on a organic compound that is not a carbon-hydrogen or carbon-carbon single bond. And they all have different names, and what happens is that these functional groups dictate the chemical reactions that the different molecules can have. So when we move forward, chapter 15, 16, 17, and 18, are actually divided by functional group. Chapter 15 is hydrocarbons, so things like double bonds and triple bonds in carbon. Chapter 16 is the halogen alkane, so having the halogens in there. Chapter 17 is going to be alcohols or carboxylic acids. And chapter 18 is going to be aldehydes and ketones, which we'll look at later. But yeah, a functional group is essentially anything that is not carbon-carbon single bond, carbon-hydrogen single bonds. Those are the functional groups in organic chemistry, and they dictate how different chemicals react. Now, in a homologous series, the only difference between all the different compounds in a homologous series are the number of carbons. So for example, here we have the simplest alcohol. This is what we call methanol, and we'll learn how to name it in section 3. But this is methanol. Methanol is a compound that has one carbon with 3 hydrogens and OH, so making it an alcohol. If we add a second carbon to the carbon chain, to the backbone that we discussed in section 1, and make it a 2-carbon alcohol with nothing else, just that OH, we just simply have added a carbon with 2 hydrogens in between the carbon and the OH. That is ethanol. This is a 2-carbon alcohol. If we add a third carbon and make it a 3-carbon chain before we have that OH, that would be propanol. Methanol, ethanol, and propanol constitute a homologous series because they're the same functional group. All we have is added number of carbons. That functional group is what determines the chemical reactions, though. So methanol, ethanol, and propanol all behave the same way. All behave the same way because we have simply one OH on them. They're all alcohols, and alcohols are all going to have the same chemical reactions. The general formula for a homologous series is given by using ends. So whenever we have an alcohol, for example, we're always going to have that OH group. So we put that separately as functional groups usually are. So we see here in that generic formula, let me use a different color. In that generic formula, we have that OH to represent that these are alcohols, that we're always going to have that OH there. And these are just different ways that you can show that OH. And then we have CnH2n plus 1. What does this mean? Cn means that if we have n number of carbons, then the number of hydrogens in that molecule will be 2n plus 1. So if we have one carbon, like we do in methanol, Then we're going to have 2n plus 1. 2 times 1 is 2, plus 1 is 3. So that's 3 hydrogens. So we have 1 carbon, 3 hydrogens, and the OH. If we have 2 carbons, like we do in ethanol, then for the homologous series here, it's going to be H at 2n plus 1. Meaning we're going to have 2 times 2 is 4, plus 1 is 5 hydrogens. And we indeed do have 5 hydrogens. 1, 2, 3, 4, 5. And again, that's separate from the OH, which is so separate here. Then if we have 3 carbons, like we do in propanol, then 3 times 2 is 6, plus 1 is 7 hydrogens. And we do have 1, 2, 3, 4, 5, 6, 7 hydrogens. So that's what a homologous series is. It's very simple. Always the same functional group with increasing number of carbons. That's what makes a homologous series. So it's mostly a vocab word that we use when we have the same type of compound with the same functional group, but with increasing number of carbons. And we always have a general formula that uses N, kind of like a mathematical equation, to represent how many carbons we have, and then from there how many hydrogens based on those carbons, and our functional groups separately. So let's look at what the functional groups are, because there are many different functional groups, and we are going to learn about all these different functional groups and their reactions individually, like I mentioned before, in the coming sections. But we're going to need to know what the functional groups are, because in the next section we're going to learn about nomenclature, how to name organic compounds, and that is very much dependent on their functional group. So what are the different functional groups we can see? Now, functional groups, like we said earlier, dictate the type of chemical reaction in an organic compound we'll have. That's why they're important, because the type of functional group dictates everything about an organic compound. In AICE Organic Chemistry curriculum, we divide up the reactions of the functional groups into different chapters, and that's what we're going to go by. Some organic compounds might have multiple functional groups and can therefore undergo different chemical reactions based on their functional group, and we'll deal with those as we go through the different reactions. But before that, what are the functional groups you need to know? Because there's a difference between all the functional groups, and there are many of them, and the ones that show up in the AICE exam. So the ones that show up in the AICE exam are as follows. Alkenes are the one functional group that is going to be part of the carbon chain. An alkene is simply a double bond within the carbon chain. So any compound that has a double bond will be considered to have an alkene functional group. Their general formulas, if there's only one double bond, and that's something we have to come to realize. All of these general formulas here that we're going to look at are if there's only one instance of that functional group in the whole molecule. So for alkenes, the general formula is CnH2n. So if there's 2 carbons, then there are 4 hydrogens. If there's 5 carbons, then there's 10 hydrogens, so on and so forth. Ethene is an example of a structure, an alkene, right? A carbon double bond to another carbon. So just to show you a few to show you a homologous series of an alkene, and I'm going to use skeletal formulas. If we have just this is CH2 in structural formula. That will be ethene. It is a 2-carbon alkene. You cannot have a 1-carbon alkene because it's a double bond between carbons. If you have 3 carbons with a double bond, that will be the next one, will be CH3, CH, CH2. That will be propene. If we have 1, 2, 3, 4 with a double bond, that will be CH3, CH, CH, CH2. Again, oops, I keep not drawing the double bonds. So that's a double bond here. That's a double bond here. Let me fix that. Because again, structural formulas, we're going to show the double bond, right? So that's a mistake I just made. So it has CH3, double bond, CH2, CH3, CH, double bond, CH, CH3, and this will be 2-butene, and you'll learn why 2 later when we do the section on nomenclature. 1, 2, 3, 4, 5, and then double bond, so this will be CH3, CH, double bond, CH, CH2, CH3. This will be 2-pentene, so on and so forth. So we can keep adding carbons here, and just with one double bond, we make a homologous series. The general formula here is always going to be CnH2n. So if we count the carbons and the hydrogens, here we have 2 carbons, 4 hydrogens. Here we have 3 carbons, 6 hydrogens. Here we have 4 carbons, 8 hydrogens. And then here we have 5 carbons, 10 hydrogens. And it's just going to keep going if we just keep adding carbons with only one double bond to make the homologous series. So these are all alkenes. Anything with a double bond in the carbon chain is going to be an alkene. The next functional group we're going to see is the halogen alkanes. Now the halogen alkanes are a little more varied because we have 4 different halogens. All halogen alkanes what's gonna happen whenever we grab one of the hydrogens and we replace it with a halogen. Halogens being either fluorine, chlorine, bromine, or iodine. Now, whenever we show a general formula, you might see the letter R used, where R is going to be just carbon chains, right? R could be 2 things. R could either be a carbon chain, so a bunch of carbons chained together, or in some cases, hydrogen. So obviously this is not a case where R could be hydrogen. An alkene is a case where R could be a hydrogen. But in a halogen alkane, the halogen X, which we always represent halogens with X, has to be attached to a carbon chain. The general formula for an alkene, a halogen alkane, is always CnH2n plus 1x. Now, why this? For an alkane is going to be just a regular hydrocarbon with single bonds. The general formula is CnH2n plus 2. So alkanes are what we call just regular carbon chains, right? Without any functional groups, just carbon, hydrogen, everything single bonded. CnH2n plus 2 is the general formula for an alkane homologous series. When we have a halogen alkane, we replace one of those hydrogens for the halogen, which we symbolize with X. And so the general form becomes CnH2n plus 1 instead of plus 2. Because we're replacing one of the carbons, one of the hydrogens, with a halogen. So, for halogen alkanes, what does homologous series look like? So if we had, for example, C, and I'm going to draw this one as displayed because we can draw a 1-carbon chain as skeletal. If we have CH, and we'll do Br, H. Right, this is CH3Br. If we add 1 carbon, so if we have 2 carbons and a bromine, so this will be, and I'm going to show one more time in displayed, and then I'm going to switch over to skeletal. CHBr, H, 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 H. So this is this. Right? So we have 2 carbons and the bromine now. So this is the second one in the homologous series. This is C2H5Br. So we have replaced one of the hydrogens. Essentially, if this was not bromine, it would be C2H6. But we replaced the hydrogen with a bromine. And that could be any halogen. If we're 1, 2, 3 Br, and again, this is not a carbon, so it's 1, 2, 3 carbons. This is C3H3, 4, 5, 6, 7 Br. Again, H is going to be 2n plus 1. 2 times 3 is 6, plus 1 is 7. 1, 2, 3, 4, 5, 6, or not 6, BR. So if we do 5 carbons, we skip 4 here, so a little skip. We have C5H. Again, 2n plus 1, so 11 BR. Why 11? You remember, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 hydrogens that we're not showing here. So it's a homologous series for a halogenal alkane. Halogenal alkanes just have a halogen where a hydrogen should be. Next is alcohols. Very similar to halogenal alkanes, only instead of the X halogen, we have an OH group. OH is what makes alcohols alcohols, and this is all the alcohols you're used to. Ethanol, isopropyl alcohol are all going to be represented by this OH group. The formula for an alcohol, the general formula is going to be the same as for halogenal alkane, CnH2n plus 1, but with an OH instead of an X. So we're replacing essentially the hydrogen with what we call a hydroxyl group. Well, let me not use yellow for that. This OH is what we call a hydroxyl group. Not to be confused with hydroxide, which is the ion. A hydroxyl group is the OH group attached to a carbon chain. That makes up an alcohol. So we already saw homologous series here. I'm going to go back for a second. We already saw the homologous series for alcohol. We have methanol, ethanol, propanone. These are all alcohols because of that OH. And so we have CnH2n plus 1. Where we have 3 carbons, we have 7 hydrogens, and then that OH. So that OH is what gives these alcohols their, the hydroxyl group is what gives these alcohols their special properties that we'll talk about in the alcohol chapter. Next are aldehydes. Aldehydes are going to have what we call a carbonyl group, and I'm going to put this up here. So a carbonyl group is a carbon double bond oxygen, and then you have R groups, either hydrogens. Remember, an R group can either be a carbon chain or H sometimes. So only sometimes can it be hydrogen. There are special, and this is one of those cases where it cannot be hydrogen. So anytime you have this carbon or this group right here, it's called a carbonyl group. This carbon double bond oxygen is called the carbonyl group. So there's a few groups that have carbonyl groups. Aldehydes, ketones, carboxylic acids, and esters are all carbonyl functional groups. So these are carbonyl functional groups because, as you can see, we have that carbon double bond oxygen in all of them. 1, 1, 1, and 1. What's going to change is what are these R groups. That's going to change between these 4. So for an aldehyde, your R group, which I'm going to put here in pink, or actually let me do blue. The R group for an aldehyde is going to be a hydrogen, and then on the other side, just a carbon chain. So remember, in this particular case, that R group is actually not a hydrogen. It is a carbon, or one of them is a carbon chain. Actually, I'm going to leave that there. Oh, no. So that, in this case, one of them is hydrogen, one of them is an R group when you have an aldehyde. This R group is usually shown in structural formulas as CHO, the CO and H. Whereas the R is the rest of it. So I'm actually going to put the R group in a different color. Let me do green. So one R group is just going to be our carbon chain in green, the CnH2n plus 1. And then the CHO is going to be our carbonyl group. mixed in with that hydrogen. All right. Then in ketones, what changes is that the R groups are both going to be carbon chains. So once we move over to ketones, and let me actually put green here. So once we go over to ketones, one of those R groups is still a carbon chain, and so is the other one. So the R groups become these carbon chains, this CmH2n plus 1, and then this CnH2n plus 1. You use different subscripts, N and M, to show the different number of carbons in both. So one could be 5 carbons, the other one could be 3. But then we still have that carbonyl group in the center. So we still have that CO in the center representing our carbonyl group. And I'm going to show you a homologous series of all of these in a second. For carboxylic acids, again, we still have that carbonyl group, the C-double-bond-O. We still are going to have a carbon chain that is going to be the main body of our molecule. That's the R. But then that other R that is no longer R, it's an either hydroxyl or a hydroxyl group, an OH. So we have this COOH that forms as part of our carboxylic acid. So we have that OH here in the name, in the functional group and structure formula, and that CO, which is a carbonyl group. And then the main part of our molecule, the main body of our molecule, is our R group, our carbon chain. And then esters are the most complex probably. Esters still have that carbonyl group, the CO. But then on one side, they're going to have an OCR or OR, which is the carbon chain that attaches to the O. So they have two carbon chains here. So we have that carbon chain that is the OR carbon chain that attaches to the oxygen. And then we have that main carbon chain we have in all of these, that is the R group. And this was flipped around a little. We have the main carbon chain as part of the O group. All right, so the carbonyl ones can be difficult to identify because they are very similar. They all have that C-double-bond-O. What changes is what's attached to it. In aldehydes, we have a carbon chain and an H attached to the carbonyl group. In ketones, we have two different carbon chains attached to the CO carbonyl group. In carboxylic acids, we have that main body carbon chain and an OH attached to it. And then in esters, we have that R main carbon chain and then an O with a different carbon chain attached to it. So let's look at what these homologous series look like. So again, I'm going to go here. So I'm going to divide my screen into 4 sections. Oh, that's my highlighter. So I'm going to divide up my screen into 4 sections. So half roughly. And then here in aldehydes, what is the aldehyde? This is going to be gen structure here. What is the general structure going to look like? Oh, and I just erased one of my lines. So the general structure for an aldehyde is going to be the carbonyl group with a hydrogen on that carbon and then some kind of carbon chain on the other side. And I'm going to show you what that looks like in a second. For ketones, we're going to have that carbonyl group with an R on one side, so one carbon chain on one side, and a different carbon chain on the other. So in general structures, usually we use a little apostrophe to show different carbon chains. So one carbon chain on one side, another carbon chain on another, which essentially makes the carbon in the carbonyl part of a much longer carbon chain. Then for carboxylic acids, we're going to have that carbonyl group with an OH on one side. So essentially think of it like an alcohol attached to a carbonyl group. And then the R group, the carbon chain, on the other. And for esters, we're going to have that carbonyl group with a carbon chain on one side, and then on the other side an O with a different carbon chain. So let's look at what some of these compounds might look like. Let's start with the aldehydes. I want to draw like 2 or 3 different ones. Let's do 2, just because of space. So an aldehyde with 3 carbons might look like this. And I'm going to draw this in, again, skeletal formula so you can start getting used to the idea. I'll draw the, actually I'm going to draw the display formula and then the skeletal. So you're going to have the CO with a double bond with your hydrogen on one side. And then you're going to have, let's say it's like 3 carbon chain. You have a carbon with the 2 hydrogens. And then another carbon with your 2 hydrogens. Or actually 3 hydrogens in this one because it's the terminal one. So this is an aldehyde because we have a C double bond OH and then a carbon chain. Again, this particular one is 3 carbons because we're counting the carbon in the carbonyl, in the double bond oxygen. But again, this could be 3, 4, 5, 10, 15 different carbons. It will still be an aldehyde. What makes it an aldehyde, again, is that structure right here. And I'm going to highlight the structure in white. So what makes it an aldehyde is this. That's our aldehyde. That's what makes it an aldehyde. So in a structural formula, I'm just going to draw one of each of these. In a structural formula, this will be 1, 2, 3 carbons. So 1, 2, 3 carbons. That third carbon has that carbonyl double bond, O. And then a hydrogen, which we don't show. So this is what it looks like in skeletal formula. CH3, which is right here. CH2, which is right here. And then that carbon double bond oxygen with the hydrogen, which is right here. Sometimes you'll see the hydrogen shown in skeletal formulas if they're a bit of a hybrid skeletal formula. But sometimes you won't. So you gotta be able to recognize it. For ketones, again, if we do a 3 carbon ketone on each side, or a 2 carbon on each side, for a ketone, we're going to have that carbonyl group, and then on each side we'll have carbons. So we might have let's do a 2 carbon chain on this side. So CH2, CH3. And then maybe a 1 carbon chain on this side. So just 1 carbon here with the 3 hydrogens. This will be a ketone. Again, what makes this a ketone? The fact that we have, our carbon double bond oxygen, our carbonyl group, with bonds to carbons. So this actually makes it part of the carbon chain because it's a 1, 2, 3, 4 carbon chain. That's our carbon backbone. So essentially, ketones are carbon backbones with a double bonded oxygen attached to them. In our skeletal formula, what that's going to look like is just a 1, 2, 3, 4 carbon chain, 2, 3, 4, with the second carbon in this case having a double bonded oxygen. So that's a ketone there. So it's very much incorporated into the carbon chain, although the carbonyl group sticks out of the carbon chain. The main difference between a ketone and an aldehyde is that the ketone is going to have the double bond oxygen in the middle of the chain somewhere, whereas the aldehyde has it at the end of the chain. Also, quick reminder, remember these oxygens do have 2 lone pairs of electrons. They're just not shown usually in organic chemistry. With carboxylic acids, we're going to have that OH. So again, these are going to end the carbon chain because they're going to not be able to keep going with that OH there. So let's say we have a 5 carbon carboxylic acid. We're going to have that C double bond O at the end with the OH. And then we'll have 1, 2, 3, 4, 1, 2, 3, 4, 5 carbons in total, with each of these carbons needing 4 bonds, so everything that's left over is going to be hydrogens. So this will be the Lewis structure, or the displayed formula, should I say, for our what we call pentanoic acid, the carboxylic acid with 5 carbons. If we draw it as a structure or for a skeletal formula, what it's going to look like is 1, 2, 3, 4, 5 carbons, with the 5th one having the double bond O and then an OH. We would actually write the OH because not a carbon, and the hydrogen because it's not bonded to carbon. So it's basically like an aldehyde in the sense that carbonyl is going to be at the very end of the chain, but instead of having a hydrogen sticking out, it has an OH sticking out, so we actually have to show it. And then esters. And esters are, and again, sorry, what makes these carboxylic acids a carbonyl group and what makes them a carboxylic acid is the fact that we have, let me make this bigger, is the fact that we have that COOH. That's what makes it carboxylic acid with our carbon chain attached. And then finally, for our esters, esters are going to have that carbonyl group, but they are going to have a carbon chain on one side. So let's make a 2 carbon chain on this side. 1, 2. So they have a carbon chain on one side of the carbonyl group. And then on the other side of the carbonyl group, you're going to have an oxygen. But instead of that oxygen being attached to a hydrogen, like it is in a carboxylic acid, it's going to be attached to another carbon chain. So let's do a 1 carbon chain here. So CH3. So 1, 2, 3. So what makes this molecule into a carbonyl, into an ester, is the fact that we have that carbonyl group. Oops, make that bigger. Is the fact that we have that carbonyl group with an O bonded to a carbon on the other side instead of bonded to an H, which would make a carboxylic acid. All right, so that's what makes it an ester. If we wanted to show an ester as a skeletal formula, all that's going to be is we're going to have our chain here. So 1, 2, 3 carbons with a carbonyl. So 1, 2, 3 carbons with our carbonyl here, and then an oxygen to another carbon. So when I draw the bond to the oxygen, and then the other carbon. Because remember, the line, if it's just a line that goes nowhere, that's a carbon right here. So this is what this ester would look like as a skeletal formula. So we can recognize those structures. So we have our aldehyde all the way on the left here, where we have the carbonyl group with a hydrogen sticking out, so that we don't show it in the skeletal. We have a ketone here in the middle, where the carbonyl is somewhere in the middle of the chain, instead of at the end like an aldehyde. We have a carboxylic acid here, where the carbonyl is at the end again, like in aldehyde, but instead of a hydrogen, we have an OH, so we show that. And then we have an ester, where that carbonyl is in the middle, that carbon double bond oxygen is in the middle, but it's attached to an O that's then attached to another R chain. So that's what makes this an ester. So these are the 4 different functional groups that all have a carbonyl group. Remember, the carbonyl group is that C double bond oxygen. So they all have that. But these are 4 different functional groups: aldehydes, ketones, carboxylic acids, and esters. All right? Now, we do have 2 other functional groups that are going to come up on the test. One of them is amines, which we're only going to look at what we call primary amines in AS chemistry. We'll look at secondary and tertiary in A-level chemistry. But in amines in AS chemistry are always going to be primary, meaning we're going to have an R bonded to an NH2. So very similar to our alcohols, where the alcohol had the OH on them, the amines have an NH2, because nitrogen needs 3 bonds, so you now have 2 hydrogens. So again, the general formula is going to be very similar to the halogen alkanes and alcohols, CnH2n plus 1. Only the difference here is going to be that instead of having that OH, we have that NH2. And then finally, we have nitriles. Nitriles are very similar in that it's something just we exchange a hydrogen for something else, but instead of an NH2 in nitriles, we have a C triple bond N. And that's usually shown in the skeletal formula, just CN. And in nitriles, we're again going to have that carbon chain, CnH2n plus 1, because we have replaced one of the hydrogens. But then we're going to have the CN instead. So it's a nitrile. C triple bond N is nitrile. Amines are NH2 that's attached to them. Alcohols are going to be an OH that's attached to them. And then halogen alkanes are going to have that halogen, that X attached to them. So these are the different kinds of structures. My suggestion is when you're trying to remember which functional group is which, separate them by categories. You have the four that are just going to replace hydrogen, which are the halogen alkanes, alcohols, amines, and nitriles. And it's just that the hydrogen is replaced with something different. And halogen alkanes is replaced with halogen, alcohols is replaced with an OH, amines is replaced with an NH2, and nitriles is replaced with C triple bond N. You have your alkenes, which are the ones that are going to be incorporated into the carbon chain, which is just a double bond in the carbon chain. And then you have your carbonyl groups, your aldehydes, ketones, carboxylic acids, and esters that we just discussed. One thing I should add that is not technically in your curriculum, but you might be asked about as an extended critical thinking question, are alkynes. Alkynes, it's supposed to be an E. Alkynes are a cousin of alkenes. Alkenes have a double bond. Alkynes have a triple bond. And then just two things coming out of this, R groups coming out of them. So triple bond alkynes, double bond alkenes, and then we discussed earlier an alkane, A-N-E, it's just single bond carbons with, other things attached to them, because these are going to have three things attached to the carbons. So alkane is just your basic hydrocarbon. Alkenes are hydrocarbons with a double bond, and alkynes are hydrocarbons with triple bond. And we'll talk more about these three and their differences once we're talking about nomenclature and naming compounds in the next section. But for now, that is it for homologous series and functional groups. I will see you all in the next video.